Hello, everybody. Welcome to today's current seminar. Today we have one talk, one speaker. Our speaker is Conor Rowan. He will be giving a talk on physics-informed solution reconstruction in elasticity and heat transfer using the explicit constraint force method. Conor Rowan is a PhD student in aerospace engineering at the University of Colorado Boulder, where he researches physics-informed machine learning for engineering mechanics, supported by the ND SEG flowsheet. He holds a master's degree from CU Boulder and a bachelor's from Dartmouth College and a bachelor's of art in mathematics from Bard College at Simon's Rock. Prior to graduate school, he worked for 3 years at Boeing Commercial Airlines. Conor is also interested in philosophy of science and complexity science, receiving the 2024 June Harper PhD Fellowship from CU's Benson Center for his interdisciplinary work. He recently attended the 2025 Complex System Summer School at the Santa Fe Institute and aims to bridge philosophy, complexity, and engineering in his career. With that short introduction, the floor is yours and you can start your presentation.
Hi everyone. Thanks for having me. It's a privilege to be here. I've followed Professor Karniadakis' work for a few years now, so it's exciting to talk to his group. So as mentioned, the title of my talk is Physics-Informed Solution Reconstruction using the Explicit Constraint Force Method. So this was already covered a little bit. I saw in some past recordings that people gave a bit of an about me slide. So I started at this very weird small liberal arts school called Bard College at Simon's Rock, where I studied math, and they didn't have an engineering department there. So I transferred to Dartmouth halfway through and studied mechanical engineering. I graduated in 2019, and then I moved over to Boeing Commercial Airplanes in Washington State. I worked there for 3 years as a production engineer in a machine shop that made wing parts and structural components for the commercial airplanes. And this is where I got interested in solid mechanics. There's a lot of cool solid mechanics problems that they work on in the factory. A lot of very hard ones. And so I spent some time studying solid mechanics and working on some metal forming problems when I was there, and decided to go back to graduate school. I started at CU Boulder 3 years ago. I just finished my 3rd year of the PhD in aerospace engineering. And as mentioned, I just recently went to a month-long summer school at the Santa Fe Institute. I'm not sure if anyone's heard of this. They do complex systems research, which is a notoriously hard thing to define, but a lot of interesting work kind of at the boundaries of science. So they're trying to do mathematical biology and networks models for social networks and diseases, economics, human behavior. It's very cool. It's very infused with computational modeling and also some philosophical questions. It's a very neat interdisciplinary place. So I'm interested in machine learning for engineering mechanics, for solid mechanics, fluid mechanics, and heat transfer. I'm also interested in, as mentioned in the bio-philosophical problems in science. So philosophy of science is a pretty old discipline. People have been talking about questions like what is a law and how do we know a law is true? And are scientific models real or are they just calculating machines? I'm not so interested in these questions as much as sort of current philosophical problems that show up in scientific research. And I think machine learning is a really interesting area for this because it changes how we do science. It changes really in very fundamental ways how laws are generated, what understanding means. We ask questions, is prediction good enough? Do we need insight into how something works in order to understand it? So for example, I've written something recently on the question of interpretability for equation discovery and symbolic regression. That's sort of my first attempt at getting involved in these sorts of questions. Okay, so on to the talk. Kind of starting at the highest level, there's 2 big paradigms as I see it in scientific machine learning right now. There's physics-informed neural networks, where a neural network is used as a discretization for a PDE solution, a PDE or ODE solution. And the physical laws show up in training, maybe some data too, but the physics are sort of driving the problem. And then operator regression, where the inverse of a differential operator is learned from labeled input-output data for some system governed by a differential equation. So I mostly work with the pins type methods using physical laws. Here's just a little chart I threw together, kind of a taxonomy of different pins-based approaches. You get different methods depending on how you set up the physics loss and the optimization strategy that you use. So the standard pins uses the strong form loss. Deep risk method uses the variational energy. There's methods that use the weak form. You can solve the system with Newton's method. You can minimize the residual of the weak form. There's been some work on encouraging temporal causality based on your optimization strategy for these dynamics problems. So there's a whole wide world of pins-based methods, so discretizing the PDE solution. But you can also use data, as I'm sure you guys all know. We can solve inverse problems where there's some missing problem parameters in the governing equation. We have some measurement data inside the domain, and we use a mix of the physics and the measurement data to come up with the solution to the PDE and also to infer the missing problem parameters. So the graphic that I have here is a conjugate heat transfer problem. There's some unknown thermal boundary condition where those green triangles are. We have some measurements of the temperature and the velocity field of the fluid inside the domain. And you can set up this kind of composite loss where you're trying to respect the data, you're trying to solve the physics, and you also have trainable parameters that are fit along the way in solving this optimization problem. So very similar to inverse problems is the problem of solution reconstruction. So I think of this as kind of the mirror image of an inverse problem. An inverse problem, you want to estimate problem parameters or a field in the example that I gave, the sort of thermal boundary condition field. But solution reconstruction, sorry, we're looking for the parameters or some missing field in an inverse problem, and we recover the solution along the way. It's sort of a means to an end. Solution reconstruction is kind of the opposite of this, is that we care primarily about the solution field, and we estimate problem parameters along the way. And you might say, well, why do we need to estimate these problem parameters? Why can't we just sort of interpolate or do a kind of regression problem on the solution field? I mean, often the physics is used to regularize the regression problem. And if there wasn't anything missing in the governing equation for the physics, you could just solve that equation in order to reconstruct the full field state. So usually there's some knowledge that's lacking, and that this sort of partially known physics shows up as a parameterized governing equation. So physics-based solution reconstruction and inverse problems are equivalent in some settings. So if we get the solution field, we also, sorry, in solution reconstruction, we get the solution field, and the problem parameters are means to this end. Inverse problems are the opposite. These two are the same when the parameterized physics can exactly recover the measurement data. So I call this being consistent with the measurement data. There's no trade-off between satisfying the governing equation and fitting the measurement data that's used. But this is not always the case, right? Sometimes the parameterized model is misspecified. That not only are we missing some problem parameters, but we might actually be missing terms in the governing equation, or we may have, for whatever reason, parameterized the problem incorrectly. So in this case, there's a trade-off between the data and physics losses. I can't simultaneously drive the residual of the governing equation down to zero and satisfy the data constraints exactly. So this might show up. The example that comes to mind for me is potentially like a digital twin or something that I have measurements of some system, and I'm trying to blend those measurements with knowledge of the physics. But the system is extremely complicated. There's a lot of physics that we might not model. Either it's too complicated to model or we don't know how to model it. And in this case, the data and the parameterized equation that you wrote down might sort of be in conflict with one another. And we have this question of how do we integrate these two things, our measurements and our knowledge of the physics, which regularizes this kind of regression problem from solution reconstruction. How do we integrate them in an optimal way? And there's this additional question too of if there's a trade-off between the data and the physics, we have to say, well, maybe willing to live with some error in the data, maybe willing to live with some error in the physics. If you're willing to live with error in the physics, there's a question of how do you spread out that error in space. So in this sense, solution reconstruction problems are kind of a unique type of problem. It's not a standard inverse problem. And then here I'm just sort of positioning my work. Well, I'll talk about the explicit constraint force method, ECFM, in this sort of broader world of scientific machine learning, where using pins for inverse problems relies a little bit more heavily on the physics in the assumption that the parameterized model is correct. It can exactly recover the data for some choice, for the right choice of the parameters. For us, with this explicit constraint force method, we lean a little bit more heavily on the data because there's some uncertainty as to the form of the physics. So just a brief overview of what we'll talk about today. I'm going to review some standard solution reconstruction methodologies. From there, discuss these two outstanding issues, and then touch on a third, although we won't get into it too much. In an attempt to remedy these two issues, we need to go through this sort of detour, which is exploring a kind of way of thinking about what's happening when you do constrained optimization in the context of mechanical systems. So we introduced this idea of constraint forces and then the minimum constraint force principle. And then with these in hand, we can sort of integrate them to introduce this explicit constraint force method, which is my notion of optimal solution reconstruction in the case of misspecified models. And then I'll give two numerical examples, time permitting, maybe just one, of how this method works. And then here's the citation for our preprint that's on archive right now. Okay, so some background on solution reconstruction. So this is the sort of high-level view of what a solution reconstruction problem might look like. We have a state of a system U of X. It's governed by boundary value problem with Dirichlet boundaries, n is some differential operator, potentially nonlinear differential operator. S of x is a source term. Omega is the computational domain. So this is the true system, which we may or may not know. And then we take noisy measurements of this solution at C sensor positions, say, we call these measurement values VI, and there's some noise, C, with a known distribution with known variance. So the solution reconstruction problem, we have a new state field Wx. This is our reconstructed solution. We have some parameters, epsilon, where that's broken out into epsilon1 and epsilon2. Epsilon1 controls the differential operator. Epsilon2 controls the source term. And this is sort of our best guess as to what we think the governing equation looks like. So the solution reconstruction problem is we want to satisfy this parameterized governing equation, satisfy the boundary conditions, which we take to be known, and also have the reconstructed solution fall within the measurement data within some range, right? Where alpha is sort of defining this confidence interval of some specified significance level around our measurements. So we just take the noise, use our knowledge of the distribution of the noise and make this deterministic inequality constraint. So just to make this a little bit more concrete, say we have this 1D boundary value problem seen here in the top line. We have a spatially varying coefficient field. We have some source term. So U satisfies this governing equation. We take measurements at C locations, in this case noiselessly. And for most of the talk, I'm not going to talk about noise too much, though we do address it in the paper. So then we set up the solution reconstruction problem. We parameterize a boundary value problem. Again, it's sort of our best guess as to what we think is going on with the underlying system. And in this case, we get it wrong, right? We miss the spatially varying coefficient. We don't quite get the source term, right? So depending on how much data you have, how big C is, we might not be able to satisfy these two conditions exactly in the solution reconstruction problem. We might not be able to pointwise satisfy the differential equation and respect the data constraint simultaneously. So this is the bind, right? This is the bind with the misspecified model. So in response to this, we need to figure out a way to distribute error, right? Do we live with error in the measurement data? Do we live with error in the physics? And if we live with error in the physics, how is it kind of distributed? So one notion of an optimal solution reconstruction or a reconstructed state field comes from the penalty method here. So in practice, we need to discretize the state field, so we call that W hat. There are parameters theta, could be coefficients on a linear discretization, could be neural network parameters, not too important at this point. So we have a penalty parameter, lambda d, and we just minimize the weighted sum of the data and the strong form loss. So we minimize over the solution parameters and the and what I call the physics parameters, epsilon. So in our case, with the misspecified model, we want to treat the data as the ground truth. And you can maybe debate this, but for me, I think this is appropriate when we're leaning more heavily on the data because the physics is uncertain. We say the data constraint should be enforced exactly. And that could be exactly the inequality constraint where the data is noisy. But we don't want this soft enforcement of the data constraint. And I'm aware, there's different approaches to modify this penalty method to drive the penalty up in a way that's optimal in order to get more accurate constraint enforcement. So that's fine. But we're going to rely more heavily on Lagrange multipliers for the first reason being that we want this exact constraint enforcement. And the second reason is that it will actually be a useful tool for us to think through some questions about how to interpret what's happening with constrained optimization going forward. So the Lagrange multiplier formulation of the problem looks as follows. We have one Lagrange multiplier for each data constraint. We're still minimizing the strong form loss, but we set up this Lagrange function and the stationarity condition of the Lagrange function in terms of the solution parameters theta, the physics parameters epsilon, and the Lagrange multipliers lambda corresponds to exact constraint enforcement and minimum strong form loss. So there's other hybrid approaches for handling the constraint that kind of blend the penalty method and Lagrange multipliers, self-adaptive pins, augmented Lagrangian, Nietzsche's method. So just to call those out. But again, Lagrange multipliers is going to be our kind of workhorse tool for thinking about constraint enforcement going forward. Okay, so the first problem with Lagrange multipliers is that they don't really give you feedback as to how good your reconstructed solution is. So I have this little example problem here. I'm not showing you any of the physics. It's sort of just an abstract solution reconstruction problem. I think the actual equations are kind of besides the point here. It's just to illustrate this idea of interpretability. So we have some measurement data shown on the left, V at a handful of measurement positions. We have a parameterized physical model, and we're trying to find the parameters such that the strong form loss is minimized and the data constraint is satisfied, right? So this is just a particular example of the objective given above for this 1D boundary value problem. So we come up with this curve, this reconstructed solution shown in red. It passes through the data. It looks pretty smooth. But we don't really know, have we found problem parameters such that we automatically pass through the data, or is this curve kind of driven by constraints, which would indicate that our parameterized governing equation is wrong, that it's really missing a lot of physics here. And if it's really missing a lot of physics, if this reconstructed solution is driven primarily by constraints, we might not trust it, right? We might not trust this red curve too much. So we're looking for kind of a quality measure of how good the reconstructed solution is. And Lagrange multipliers don't provide this to you in any straightforward way. So that's what I mean by it not being an interpretable reconstruction, is we don't have this quality measure. So there's a second issue, which is robustness. And by robustness, I mean that the reconstructed solution is robust to your choice of physics loss. So up until now, we've been talking about the strong form loss. Many problems in engineering have variational formulations too. So there's an energy of some sort whose minimum corresponds to satisfying the strong form loss. It corresponds to a solution equilibrium configuration of the system. And for many of these problems, it's significantly simpler to use the variational form. For example, on hyperelasticity, it's much simpler to write down an energy whose minimum governs static equilibrium as opposed to writing down a strong form loss. So it turns out that using the variational energy doesn't work to reconstruct solutions. So I have an example here. I think it's the same example. A similar example. So we have a number of measurement points. We're minimizing the energy, the variational energy pi, over both the solution parameters theta and the physics parameter epsilon. And we see that smaller energies correspond to these kind of strange, unphysical reconstructed solutions. So the one shown in yellow here with the dotted line. So it turns out you can keep driving the energy down, and it actually diverges, that you keep finding larger and larger physics parameters that correspond to less and less physical reconstructions. And the variational loss does not work for solution reconstruction. So in that sense, it's not robust, right? If we it seems like kind of an innocent choice to choose the energy over the strong form loss, but we get totally different solutions. So that's part of the second issue. And then there's another problem, or at least sort of kind of perplexing detail to consider, which is that even for a simple constrained optimization problem with no physics parameters to fit, the solution is very sensitive to which loss we use. So if I just have written down a particular example here, if we use the strong form loss with two boundary conditions on the left and right, and then a constraint in the center, we get the curve shown in yellow. And so that's minimizing the error, the strong form error. And if we use the energy shown on the right with the same two boundary conditions and constraint in the center, we get the curve in red. So not only can we not do solution reconstruction with the energy, but there's kind of weird problem that doing even a simple constrained optimization problem with the two different losses leads to very different solutions. So these two or three, depending on how you count, kind of problems that we've raised, addressing them will kind of pave the way for a solution reconstruction methodology that has a lot of the features that we want. So this was a number of months ago, kind of the impetus for me to dig into these problems. Okay, so we want a solution reconstruction method that's interpretable in the sense that I just talked about, that it has a quality measure, tells you how trustworthy the reconstructed solution is. It's robust, meaning that if we choose to use the strong form loss versus the energy loss, we don't get significantly different reconstructions. And also data consistent. So this is the third criteria that I said I wouldn't talk about too much. But the idea with data consistency is that in certain simple situations, it leads to identifiability of the physics parameters, epsilon. And we'll, I think, maybe circle back to this at some point later on. But I'm going to focus on the first two here. So Professor Karnidakis has done some work on misspecified models. And I see this past work as primarily addressing the interpretability question, to think about sort of what's going on, how to think about how good your reconstructed solution is when the model is misspecified. But I think there's more work to be done on this sort of robustness problem to understand why is it that the energy and strong form loss have such different behavior. So we introduce the explicit constraint force method in attempt to remedy these issues. And this turns out to require a pretty deep study of constrained optimization. And for now, we focus on static boundary value problems in elasticity and heat transfer. Okay, so this is the explicit constraint force method, ECFM. So this is kind of a claim that constraints are enforced by introducing source terms into a mechanical system, but I think it's a fair claim. And I call this kind of a philosophy of constrained optimization because thinking about constrained optimization as being driven by additional source terms may not actually change how you do constrained optimization, but I think it does change how you sort of make sense of and how you interpret what's happening with Lagrange multipliers, to some extent with penalty methods, and certainly with my this ECFM methodology that I'm going to talk about. So the idea is that when we have constraints, we introduce these new source terms into the system, and the magnitudes of these source terms are determined such that the equilibrium configuration of the new system, new meaning that there's these new source terms, satisfies the constraints. So we sort of push on the system such that the constraints are satisfied. And this is actually kind of familiar from contact mechanics and incompressibility in fluids, though it doesn't often go under this name, that in contact mechanics, you explicitly prescribe conditions on the stress tensor at the surface of a body to prevent two bodies from penetrating each other. And in fluid mechanics, the pressure you can think of as kind of a constraint force to handle the incompressibility condition. So it turns out that the nature of this source term that's introduced to handle the constraints, it depends on a lot of things that are kind of outside of your control when using Lagrange multipliers. You don't get, in other words, you don't get to specify what this source term looks like when you use Lagrange multipliers. So here's an example from linear elasticity. We have the variational energy, and we start with the variational energy, and then we from there build a Lagrange function that enforces a fixed displacement along some patch of the surface of the body. So lambda is the Lagrange multiplier here. And you can see just kind of by analogy that the traction T and the Lagrange multiplier lambda both kind of have the same form. They both involve surface integrals over that quantity dot product with the displacement. And you can see that the U naught, the prescribed displacement, drops out when you take a variation, which the variation of this Lagrange function is the equilibrium condition for the system. So here, the Lagrange multiplier is a constraint force. It works as a constraint force. Its magnitude is determined such that the prescribed displacement is enforced, and it behaves like a surface traction. And we can just see this by looking at the energy. The surface traction and Lagrange multiplier, they have the same form. We might ask, well, what happens if we use the strong form loss as opposed to the variational energy? So here I'm sort of being a bit sloppy in ignoring the traction boundary condition. It's not really the point. So we write down the strong form loss, the divergence of the stress tensor plus the body force squared. We integrate this over the body. We're trying to minimize the strong form error, but we still have this constraint on the displacement along the surface. We throw that in there, build the Lagrange function, and now it's not clear what kind of source term the Lagrange multiplier is scaling, simply because there's no term in this loss that we can interpret that has the same form as the Lagrange multiplier. So it's not clear. It's not clear by inspection what kind of constraint force is showing up to handle the constraint. And as I mentioned, contact formulations can avoid this by specifically prescribing conditions on the stress tensor to enforce that the contact pressure is a surface traction, which physically makes sense, right? That there's some stress introduced at the surface of the body to prevent or to enforce the contact condition. Just because it's not clear by inspection doesn't mean that we can't try to figure it out. So here I now kind of familiar, hopefully looking abstract boundary value problem, though there's no physics parameters, so it's not a solution reconstruction problem. It's just a constrained optimization problem. So we can try to do some work to figure out what form the constraint forces have. So we discretize W, our state field, again in terms of parameters theta. We have a constraint somewhere interior to the domain at these C sensor positions. And we build the Lagrange function corresponding to the minimum strong form loss. And then we write out the KKT conditions, the conditions for the Lagrange function being stationary. And I package them all into this big system of equations here. So the derivative with respect to the solution parameters gives you, again, kind of the equilibrium configuration for the system. And then the derivative with respect to the Lagrange multipliers gives you back the constraints. So that's what's shown in the bottom of the system of equations here. And highlighted in red is the Lagrange multiplier term. So we don't know how this is pushing on the system right now. We need it to sort of sit alongside the body force B in order to interpret it as a source term. And right now it's not doing that, right? So this is all kind of abstract at this level, but maybe we can do a bunch of manipulations to put it inside, to put the Lagrange multiplier term inside along the other source term. And this would reveal sort of what spatial form the constraint forces have that the Lagrange multipliers are scaling. So if we could do this, it would show that the Lagrange multipliers are introducing these new forces into the system. And if we could look at this form of F and get insight into how the constraints are handled. But obtaining this, in general, obtaining a closed form expression for the constraint force F is not trivial. I've only done this for one example, which we'll show. And even for that simple example, it's pretty involved. But the point is not to take a bunch of different physical models and figure out, well, how do Lagrange multipliers introduce constraint forces for the strong form and the energy? That's not so much the point. The point is the idea that constraints are enforced by pushing on the system with these new source terms. And importantly for Lagrange multipliers, that the form of that source term is out of your control. So we might say, why not just explicitly introduce these constraint forces? It seems like going through Lagrange multipliers is just a means to an end of getting to this system of equations where there's some new forcing added with unknown magnitudes, and the magnitudes are determined through the constraints. So this is the idea of explicit constraint forces. So maybe we want a radial basis function or a hat function or a point force or some particular kind of constraint force. We can just introduce that explicitly into the system. So now this is it's breaking Lagrange multipliers a little bit because there's no Lagrange function that you can form whose derivatives give you back this system you're looking at now. But I would say doesn't matter, right? We just need these source terms in order to handle the constraints.
Conor, can I make a comment?
Sure.
So in this form, this reminds me of the Lagrange multiplier method of Joseph and Glowinski, which they use it to deal with complex geometries.
It's not. I haven't encountered it. What do they do?
It's also in variational form and so on. But basically, you instead of a they also in this way you can track particles, for example, in a flow and so on. But there is very, very similar to. So basically, you're trying to find lambdas so that you find the solution in lambda i's because you have a certain shape, the domain, right? For example, so either for complex geometries or for particle tracking or bubbles and so on, the formulation is quite similar, I think. Of course, they're not using neural networks. This is a finite element formulation that they are doing. But this Glowinski is Joseph and Glowinski. It's like 15 years ago, maybe.
Okay. Yeah, I should look into it. It's not something that I've encountered. Yeah, I mean, it's definitely similar to contact formulations with like I mentioned with prescribing conditions on the stress tensor. That's kind of an explicit constraint force in some sense, although that's not how they talked about it. But okay, so this hints at the interpretability issue that we raised earlier, where now we might get the sense that the magnitude of the constraint forces is kind of telling you something about how consistent your governing equation is with your measurements. So for example, if all of the lambdas, which are now not Lagrange multipliers, right? They're just constraint force magnitudes, are zero when you find a solution to this system of equations, it means that a solution to the differential equation automatically satisfies the constraints, that there's no inconsistency between them. Conversely, if lambda is very large, we get the idea that the system requires a lot of additional forcing in order to satisfy the constraints. There's this kind of big error in the physics which points at this inconsistency between the physics that you've written down and your data constraints. And importantly, lambda has meaningful units now. Lambda has the same units as B, right? So if it's a heat transfer problem, it's a heat flux. If it's a solid mechanics problem, it's a force or a volumetric force or something like that. So we actually know what a large or small lambda value is now, to the extent that we know what a large or small force is. So this is kind of helpful for the interpretability problem. Okay, so related to this, building on the constraint force idea, is what I call the minimum constraint force principle. So I'll show in a second a particular example. We're doing solution reconstruction with a strong form loss and Lagrange multipliers to enforce the constraint. Corresponds to minimizing the magnitude of the Lagrange multiplier. So this is like saying find the physics parameter epsilon such that the constraint force, which is determined by lambda, is minimized. So this maybe makes some sense that we want to find, intuitively, it makes some sense that we want to find our physical model, which requires the least amount of additional sort of forcing on the system such that the constraints are satisfied. And it turns out there's no property of this sort for the variational energy, and this explains why the energy doesn't work as a solution reconstruction methodology. I can drive the energy down, at least for the particular example I showed you. And I keep getting larger and larger constraint forces, which intuitively you wouldn't want, right? Why would I choose a physics parameter that I need to push extra hard on the system in order to satisfy the data constraint? It doesn't make that much sense. But this property just happens to be built in to the strong form loss, and it not in the energy. So this is, and we'll get into the details a little bit more, but an explanation for why the strong form loss works to do solution reconstruction and the energy doesn't. Okay, so this is what I mentioned of even the simple problem being somewhat involved. What we're trying to do is to first figure out the form of the constraint forces, maybe just out of curiosity. So see what kind of constraint forces Lagrange multipliers gives you for this simple 1D elliptic problem. And then secondarily, illustrate this minimum constraint force principle. And we'll use these two things afterwards to develop the explicit constraint force method. So the equilibrium configuration, I should go back to this. So here's the Lagrange function for the kind of solution reconstruction problem. We've parameterized the source term in its magnitude. We have Lagrange multiplier lambda. We have measurement V, and the measurement is taken at a point xc. So it's this simple single measurement, 1D problem, one physics parameter. And we just want to use this as sort of a toy model to explore what happens, what the constraint forces look like. Okay, so the equilibrium configuration of the system is obtained from taking a variation with respect to the state field W. So this is what we get here. We have this Lagrange multiplier term kind of sitting outside. So we note that you can take this Lagrange multiplier term that's about the variation is evaluated at the measurement point, and we can integrate it against a delta function centered at the measurement point. So step one, we put it under the integral. We're trying to make it look like a source term. Step two, we note that the delta function can be written as a second derivative of this kind of ReLU type function, which I'm going to call I going forward. So it's just 0 up until xc, and then linear after xc. So you get the delta function when you take two derivatives of the kink at that point. Okay, we've gotten the second derivative out because we ultimately want we have the second derivative on the variation here, so we're sort of aiming at that. We put it under the integral, so we want to further manipulate this such that the Lagrange multiplier looks like it's scaling a source term of some sort. Okay, so we integrate by parts two derivatives from the indicate or the I function, the ReLU type guy, onto the variation. So we get this boundary, one single boundary term that shows up. We use the fact that the variation is 0 on the two boundaries. It's a homogeneous Dirichlet boundary conditions. So the variation is also 0 along the boundaries. So we're sort of almost there. We have the second derivative of the variation. This is getting close to being able to put this term alongside the source term in the equilibrium condition. We need to deal with this boundary term. So that's this one on the right here. So we use the fact that it's not important that this function here is the variation, but we just use this identity. And this allows us to write the boundary term as also showing up under an integral here. And I'm sure this is sort of a little bit confusing to look at, but you could sit down and work it out. And ultimately what we show is that the Lagrange multiplier term that we got from taking a variation can be written as something under an integral that's multiplying the second spatial derivative of the variation, which means that it looks like a source term now. So here is the rewritten form at the bottom with the constraint force shown in red, scaled by the Lagrange multiplier. So what does this look like? They look like these kind of hat functions with 0 boundaries that are centered at the constraint position. So the kink in the hat function is the location of the constraint. So this is not a general result at all. This depends on everything you could think of. It depends on the boundary conditions for the problem. It depends on the physics. It depends on all sorts of things. It's just an interesting example, I think, to illustrate what it looks like to sort of tease out the form of the constraint forces. Okay, so now with some insight into what the constraint forces are doing, we can kind of reformulate this Lagrange multiplier problem that came from solution reconstruction. If you remember, we're trying to minimize the strong form residual in terms of both the solution, W, and the physics parameters, epsilon, and satisfy the data constraint at the same time. So we can use the equilibrium governing equation to write the strong form residual in terms of the constraint force, right? The constraint force is now the mismatch. It's the error, right? In the governing equation. So previously here we had the residual, the strong form residual, and now we say we can replace this with the constraint force so long as W and epsilon are such that the equilibrium configuration is satisfied. And then we also have still the data constraint that we need to satisfy. So the minimization now is only over epsilon. So this is saying find epsilon such that when the system is in equilibrium with this sort of Lagrange multiplier constraint force, the Lagrange multiplier is minimized. This is the minimum constraint force principle. Again, this is maybe a little bit hard to see just on the slides, but it's something if you kind of write it out and play around with it, you get a better sense of what's going on. The idea here is that you can satisfy the equilibrium configuration for any epsilon. So if I have a wildly erroneous epsilon, I make it huge or something, there's some Lagrange multiplier that will enforce the data constraint, and the system will still be in equilibrium. But which one do you want to pick among all of the epsilons? You want the one where the minimal amount of pushing on the system is required to satisfy the data constraint. So that's what this equation here is saying. That's all the minimum constraint force principle is saying. It's the best physics parameter is the one that minimizes the constraint force. And again, this is not true when you use the energy as an objective. So now we do something that feels hopefully pretty natural, which is combine this minimum constraint force principle with the idea of explicit constraint forces. And that leads to the explicit constraint force method. So I'll just read this because I don't think I'll be able to say it better than I wrote it here. The intuition is as follows. Find the physics parameters epsilon such that when the solution parameters theta, the discretized state field parameters, and the constraint force magnitudes lambda jointly satisfy equilibrium, the total constraint force is minimal. So we explicitly introduce constraint forces now. There's no Lagrange multipliers anymore. The lambda are the magnitudes of the constraint forces. And we say, find the epsilon such that the total constraint force is minimized. So that's all this is saying here. Here is an expression. I mean, I'm choosing to do the squared magnitude of the constraint force. You could maybe argue that there's other better measures. It's just some measure of the size of the constraint force, such that lambda and theta are determined through the equilibrium configuration, which is shown here, right? So this is minimize the strong form loss with these extra constraint forces that we've explicitly introduced, such that the constraint force magnitudes are determined in order to satisfy the data constraint. So this is it. It combines the minimum constraint force principle with the idea of explicit constraint forces, and all of this is kind of implicit in the strong form objective that we had constraint forces from Lagrange multipliers. We sort of automatically got this the minimum constraint force idea. But now by making these things explicit, we have maybe a lot more freedom to change the constraint forces, to use different physics losses. We could use the energy now, for example. And I think another benefit is just kind of getting clear on what's actually going on under the hood in these kinds of problems.
Can I ask a question?
Sure.
So computationally, the cost is the same because you, or even more because you do have to differentiate with respect to the parameters there. So R is not the residual, is the dd theta of the residual.
Right.
So which you used to do. And now you do an extra minimization. And from what you show us, that is not necessarily a smooth integrand, right?
I guess the constraint forces need not be smooth, but they also don't depend on the parameters.
Oh, gammas are not smooth. Yeah. Okay.
Yeah.
But yeah, that's why I said the integrand itself is not smooth then.
Yeah.
But lambdas, you didn't say if lambdas are continuous or what kind of continuity you require for this minimization, because we don't know if it converges actually, right?
I don't know. Yeah. I haven't done any kind of convergence analysis on it. Lambdas are just scalars, right? These are just some
Scalars, but are functions of epsilon. So are they continuous? Are they elliptic continuous? Or what type of continuity you require for them?
I couldn't say. I don't know what kind of continuity their dependence on epsilon I have. It's not something that I've looked into.
Okay. Yep.
But yeah, so it's true that the computational cost is more. And it's certainly a this is actually kind of what I'm getting out of the next slide. So this is a lot more complicated than just writing out the strong form loss with the data penalty, for example, writing out the strong form loss with Lagrange multipliers. But I think it's important to be clear that this is kind of what's happening anyway when you're doing this strong form loss with Lagrange multipliers. And it happens to be a very convenient way to incorporate all of these ideas into a pretty kind of concise, simple loss. The problem is if you want to change things a little bit, the solution reconstruction problem kind of breaks. So again, if I want to use the energy as opposed to the strong form loss, it breaks. And that's, as I mentioned, kind of what inspired this work, is this recognition that actually this problem is kind of sensitive to how you set it up. And we were curious to figure out why, and to how to remedy this kind of sensitivity. So I would say whether you choose to use this method or not, I think it's beneficial to have some insight into what's going on. And a potential benefit is that you get to choose how the error is spread over the system, which is the same thing as saying you get to choose the constraint force, right? So if I do it with the strong form loss, yes, it's simpler. I don't have any control over what the constraint forces that handle the data constraint are doing. And again, yeah, I say it's a philosophy because I think it's sort of a way of thinking about constraint optimization as much as it is an actual method. Okay, so let's see what kind of time I have. I'll just quickly go through this one and then spend a bit more time on the other. So this is neo-Hookean hyperelasticity. It's a bar problem. This is one of the first numerical examples from the paper. So we write out the energy for the particular energy for compressible hyperelasticity, and we show that we can use now the energy objective, which is good. Like I mentioned, it's much simpler to start with an energy and hyperelasticity, especially for the 2 and 3D potential energies. So we also devise a method for handling inequality constraints, which I think is pretty interesting because you're having to do inequality constrained optimization without relying on Lagrange multipliers when doing this explicit constraint force stuff. I'm not going to talk about that now. If you're curious, it's in the appendix of the preprint. And then the other thing that we do with this example is show that it's simple to incorporate prior knowledge about constraint forces when using ECFM. So the idea here is that there's a point reaction force at the center, and that we want to be able to encode that in our reconstructed solution in some way. And it sort of, you would have to do something like introduce explicit constraint forces in order to encode this prior knowledge about a constraint force. So just here's the sort of quick example here. We have some noisy measurement data. We have an exact solution shown in yellow in the dotted line or in the dashed line here. And then we show using this sort of penalty, the standard pins type penalty approach with a strong form loss and a penalty on the data. You have no way of kind of reproducing this kink in the displacement at the center. Whereas if you have control over the constraint forces, I can introduce some sort of really localized force at the center, find its magnitude such that the data constraint is satisfied, and I get closer to the exact solution. Though there's no reason to expect to get the exact solution when you have noisy data or when you have misspecified physics. I mean, how could you have written down the wrong equation, interpolate the data, and expect to exactly get back the model that actually generated the data? I mean, if you had a lot of data, maybe, but this makes it a bit delicate to compare different methodologies for solution reconstruction in the misspecified model case, is because it's not clear that the error with the true solution is actually a good measure of how your method is performing. It could, in some cases, it might just be random chance that you happen to be close. So we talk about in the paper, we're not really going for, we're not necessarily going for minimum error with the exact solution. We're going for a method that is, as I mentioned earlier, interpretable. You have a quality measure. It's robust in that it's not sensitive to your choice of physics loss. And then also it's this data consistency thing, which I'm sort of probably not going to talk about. But in other words, there are measures other than your error with the exact solution that I think are relevant for judging how your solution reconstruction methodology is performing. Okay, so the other numerical example talk about here is this advection diffusion system. So it just has there's some advection velocity that's constant, a of x. There's a temperature field, u. There's a source term, s. We have 0 temperature boundary conditions. The computational domain is a unit square. Discretize the temperature field with just standard multilayer perceptron neural network and build the boundary conditions into the discretizations just because it's simple to multiply by some function that handles the boundaries in this case. So this is the true model. This is a true model from which we'll take measurements. So I just generate a reference solution by doing a standard pins kind of approach, just minimizing the strong form loss with atom. I cut it off once the residual of the PDE falls below some threshold, some small threshold, and sample the reference solution on this uniform measurement grid that's shown in the plot. So this is what's going to be used for the constraints on the reconstructed solution. Okay, so this is the misspecified model situation. Instead of, say, parameterizing the advection velocity, we say, well, maybe this behavior that we see is generated by some sort of non-constant coefficient field. So the source term is known, but there's some other missing physics that we don't know. We maybe take a guess. We say, I think it's the coefficient field. In this case, we're wrong. And we're going to see how this method performs and specifically how it compares to this standard penalty method here. So again, the boundary conditions are built into the domain. We have these noiseless constraints from the reference solution. And for the explicit constraint force method, we use radial basis functions that are centered at the constraint locations in order to satisfy the constraints in this situation where there's no epsilon that we can choose such that a solution to the governing equation reproduces the measurement data. This is again the tension between the data constraint and satisfying the physics. Okay, so the first method we do as kind of a baseline is a penalty method. So we reconstruct the temperature field just by writing out the strong form loss and adding in a penalty with the data. We try this out with 2 different penalties. And you see that the loss doesn't drop to 0. So this is, again, the physics plus data loss doesn't drop to 0. And this is indicating the trade-off between these two, right? So this is the clear warning that you have a misspecified model. So I'm showing the system residual here and how it's sensitive to the penalty parameter. This will be relevant in a second. So the system residual is just defined as the sort of the error that we can't account for by choosing the physics parameter epsilon. And this in this case is coming from the sort of, I put in air quotes, constraint force is coming from the penalty method now. And this is a little bit more complicated to think about what the constraint force is from a penalty method versus Lagrange multipliers. I talk about it a little bit in the paper too. It doesn't have so neat of an interpretation as this sort of be relevant here too. So then we solve the problem with the explicit constraint force method, minimizing the constraint force, find the physics parameter such that the constraint force is minimized, the governing equation is satisfied. So for this particular example, you can look at the 2 reconstructed solutions from penalty method and my method here. They're not that different. And this is not surprising. It's not that surprising because we use radial basis functions as the constraint force, which are smooth, generally pretty smooth, given the ones that I chose at least. And the constraint forces that come from the penalty method are, again, you sort of have to trust me on this, but also smooth, right? So we can see this in the residual here. The residual is sort of, again, what's not being accounted for by choosing the right epsilon. The residual is spread out in different ways between these 2 methods, but there's certain similarities between them. And namely, one is not super localized and the other one super spread out. They have this kind of similar structure. And this is why the two reconstructions look similar. But say, for example, we wanted to use the residual in order to try to estimate or understand what kind of physics we didn't account for. So we do some kind of fitting process on the residual in order to update the model. In the case of the explicit constraint force method, the system residual and the constraint force distribution are exactly the same, kind of by definition, with very, very sort of minor errors. And it also has a very clear interpretation. This is a missing source term, right? With the penalty method, the interpretation is not so clear because the penalty, you didn't control the constraint force, and two, you kind of change the system by having the displacement squared in there. It's maybe not so obvious without writing it out. But the point is that the residual is not, you can't interpret the residual from a penalty method as a missing source term. It's a bit more complicated than that. So we actually show here that this neat interpretation of the residual as a missing source term allows you to better estimate the missing physics. So say we look at this residual and think, oh, maybe there's an advection velocity, a constant advection velocity that we didn't account for. And we can just do some least squares type fitting in order to try to recover what the advection velocity components that would explain this residual. And we see that using the penalty method, as I increase the number of data points, I don't really converge on the true advection velocity, which is 5. Whereas when we have this neat interpretation of the system residual as the sort of missing physics in a straightforward way, as you increase the number of measurement points, you get closer and closer to recovering the true advection velocity. So this is kind of a consequence of interpretability. And then I'll wrap up. Oh, it's been an hour. So solution reconstruction is not a standard inverse problem when the physics is misspecified. That's because we expect this trade-off between the physics and the data constraint, right? And we need to think about how we handle this trade-off. Constraint forces provide a nice physical interpretation of what's going on with constraint optimization, and the minimum constraint force principle gives you a notion of what a good reconstruction is. So as I've said a bunch of times now, this method allows you to use different loss functions, the energy, the weak form, the strong form without changing anything. It's insensitive to the problem formulation and also more interpretable in that you have a quality measure, which is that the magnitude of the constraint force tells you how sort of far off your parameterized model is from being able to reproduce the data. So the bottom line, in my opinion, is consider using this method when you want a clear quality measure of your how good your reconstructed solution is. When you want to incorporate prior knowledge about the constraint forces, like we did with the point reaction force, or when you're going to use the residual to update the model to estimate the missing physics, having this clear interpretation of the residual as a constraint force or a sort of missing physics will help you better update your model. And also, I just think it's kind of neat to better understand some of the moving parts of constrained optimization for mechanics. So thank you for listening to my full hour talk here that went fast. If you want to talk about this or anything else, please don't hesitate to reach out. I have a personal website that I have all sorts of random things on if for whatever reason you're curious. And then I've done some recent work on pins for eigenvalue problems and this interpretable equation discovery thing that I mentioned in the beginning that are also, they're both on archive right now. So happy to have any discussion or take any questions now.
Thank you so much for your talk. Now we open the floor for questions. Do we have any questions for the speaker? Yes, George.
Well, maybe Juan can make a comment about how he interprets his lambdas. I don't know. He's writing a paper on it.
Oh, hi, Conor. This was a really nice presentation. Yeah, in this case, you're analyzing the lambdas from the augmented Lagrangian perspective, right? You're considering that this use Lagrange multipliers. However, I noticed that sometimes when you choose these lambdas right, you get another types of benefits. Like for example, like the overall variance of the residuals decreases. So you get it's likely because usually when you obtain when you're trying to integrate, like the way that you train your models usually take the L2 norm of the residuals, assuming that you're going to the strong form. I know that you're not doing that exactly because you have like this mixed formulation, but what we usually do is like you take Monte Carlo and then with Monte Carlo use Monte Carlo approximation, right? And then in Monte Carlo approximation, the quality of your approximation is somehow related to the variance of the function that you're trying to approximate. Actually, there's like this thing that's called the law of iterative logarithms, and they tell you some type of asymptotic convergence rate of Monte Carlo, and then it's related to the variance. So what we were like somehow exploring a little bit was like that these multipliers actually help you reduce the variance, and with that, it help you get like a better approximation error.
Using which method? The augmented Lagrangian?
Yeah, you have your Lagrange multipliers, right?
Yeah.
You relate them a little bit with I think in one of your first slides that you mentioned about this, you said related to the self-adaptive peaks.
Yeah.
Right. Yeah, the thing is that you can rewrite the problem, let's say it in that way, but it's still working on the strong form, not in the weak form as you're doing.
Why do the multipliers reduce the variance of the function that you're trying to integrate?
They are trying to penalize if you go for the self-adaptive pings, for instance, where we work with something that is called residual-based attention method. That is, it's slightly different because then we work with the magnitude of the residuals themselves. But
Right.
usually, what you do is like you penalize the higher residual points, right?
I see.
So yeah, so if you penalize it's like if you have like this hilly landscape and then you're pushing down all the hills
I
first,
see.
then you
Yeah.
effectively reduce the variance.
And then also you get this benefit that you get better convergence with your Monte Carlo integration because the function you're integrating is simpler or has
Yes.
variance then. Yeah.
Yeah. That's essentially because when you do Monte Carlo, that what you said is like essentially the variance of the function that you're trying to integrate is what determines how good your approximation will be. And
Right.
essentially what you say, the function becomes simpler, yes.
Yeah. Yeah, I guess for me, what I would, think about is in what way are you pushing down those hills, right? That's sort of the constraint force idea is and what kind of forcing is being applied to the system to push down that residual. And if you use explicit constraint forces, you can control that. And if you don't, you're beholden to whatever it happens to be given the loss that you've set up.
Yeah. Yeah, that's true.
I mean, not to be confused that the setup is different. What Conor is doing is using a misspecified model. So he's looking for the missing terms, which is
Right.
different than imposing a known term. But there is a little bit of similarity. I think Nikhil had a question.
Yeah, hi, I'm Nikhil. I'm a PhD student and I work with Professor Kaniadakis. So I have a question. So when you mentioned about gamma, right? So your interpretability is also depending on what choice of gamma you use, right?
Yeah.
So I was just wondering that how, like, if you perform in numerical experiments to see like what exactly you see these effects of choosing the gamma, like what exactly should be your gamma, or like how to interpret how the physics is missing in choosing this gamma.
Yeah, so I guess two things. The most obvious answer is maybe you know what it is, right? Maybe you like that's the example with the hyperelastic bar. Maybe you know that there's a constraint force that's a point reaction or something. In that case, it's pretty easy to choose, right? Because you have prior knowledge and you incorporate it. I don't know that that's most situations. So then the question is, how do you choose it when you don't know? And this is actually getting to the data consistency thing a little bit. In 1D, to me, it seems pretty clear that like a finite element, like a linear finite element interpolation is a pretty good choice of a constraint force. just because it's kind of very parsimonious in some sense that I have I'm building this finite element approximation of the missing physics, and there's no more oscillations, for example, in that interpolation than the data suggests, right? So in other words, I think you should choose something that's parsimonious, right? I wouldn't choose like a high frequency Fourier basis or something as a constraint force because I have no reason to think really that there's a lot of oscillations in a solution unless I had prior knowledge. So I center them on the constraints. That seems natural to me that there's kind of there's the sort of the data is driving the system so that the constraint force is centered on the constraints. And then I would choose them to be parsimonious in that they sort of introduce the smallest amount of assumptions about the missing physics. So that for me, that means mostly sort of low frequency kind of behavior. But I think it's an interesting thing to do a more thorough study of different constraint forces and how they affect the solution. And maybe there's principled ways of choosing them. Maybe you could parameterize the constraint forces themselves and try to choose the parameters of the constraint forces such that the physics loss is minimized or something like that. So there's potentially more work to be done here, but I would say in general, the bottom line is they should be parsimonious because then you're not introducing extra sort of assumptions about what the residual looks like. Does that make sense?
One thing to add to that is that the type of the function that you choose obviously is going to affect the quality of the reconstructed solution. So that's part of the whole game. But one thing that is specific to this approach is that if you notice the missing representation is sum of lambda i's times these basis functions. And that is basically an indication that the quality of this missing term has to do with the size of the data. So as you have more and more data, you'd be able, I mean, depending on what basis you choose, you're going to be able to get a better resolution of this missing physics. So this is one thing that, we think is an interesting aspect of this. You can obviously introduce, let's say, a neural network for modeling the whole thing. But if you get only one or two data points, can you somehow, get an accurate estimate of that missing term? In this case, we don't go to that because we have only two terms in that representation. So basically, the size of the data indicates and determines the resolution of this missing term.
Thanks. That clarifies. Yeah. Thank you.
Conor,
I also want.
go
Yeah,
ahead, Nikhil. I thought you were
I
done.
have
No,
one.
go ahead.
Yeah, I have one more question. So, like, if I was thinking about if you have, let's say, heterogeneous material, right, and you're trying to solve for that case, uh, um, will you think that the effect of heterogeneity in the material property would show up in this case because you are trying to explicitly, in a way, modeling that, like, trying to compensate for that case? Like, I was just thinking out of loud. If you think about that way, like, you assume that material to be homogeneous and solve for it, and let's say material is heterogeneous, so will it show up here somewhere in your explicit forces, like in terms of epsilon?
Yeah,
over
yeah.
there?
So you can correct me if this is wrong framing the problem, but it sounds like maybe you assume that the material is homogeneous and it has some unknown constant coefficient, whereas in reality, the problem that generated the data had a heterogeneous material. So that means that there's no choice of constant material, probably, that will exactly reproduce the data. That means that you need these constraint forces in order to match the data. And yes, it would show up. I just think of it sort of intuitively as you need to push on the system in some way in order for it to satisfy the data constraints. And then you would have this residual from the constraint forces that you could then maybe use to estimate the nature of the heterogeneous material if for whatever reason afterwards you got the idea, oh, maybe I screwed up and there was some spatially varying material. If you wanted to estimate that, you could use the error that you get from your constraint forces to come up with an estimate of what was missing.
Yeah, thanks for clarifying it. Very interesting talk. Thank you.
Thank you.
So Conor, one more thought that I had. And you mentioned our paper on misspecified models.
Yeah.
We treat as uncertainty, but what we do there, we also add plus S of X, a source term, which is okay. So now you take S of X and you write as sum of lambda i's times a radial basis, for example, here. But you can we do a neural network, but actually you can write a neural network as a sum of the linear weights of the last layer, Wi,
Yeah.
linear, times the bases, which are the functions of the last hidden layer.
Right.
So it's a similar parameterization, although overall the formulation is not the same because then you do, but like since you talk about philosophy, it's the same sort of philosophy, because then these weights of the last layer will depend on epsilon.
Right.
And basically you're solving that problem. Are you adjusting the magnitudes?
Right.
Here you adjust also in the neural network, you adjust the base at the same time, but
Right.
It is the same interpretation. I think it's just that I think your overall formulation is different. You know, when you take the two minimization problems from what we did, but otherwise I think it's the parameterization is similar. It's just the execution is different.
Yes, I agree. The one that we didn't talk about it, but the data consistency thing, Alireza just kind of nodded to a minute ago. There is a difference in that the number of parameters in my discrepancy model matches the number of data points that you have. Whereas if you use a neural network, it's sort of over parameterized.
Yeah.
Which, that's fine, I guess, if you sort of want to rely on like a spectral bias or something to give you low frequency interpretations. But for example, if I had a Fourier basis, I use some big Fourier basis for my discrepancy model. It being over parameterized could lead to sort of very strange sort of interpolations where there's high frequency behavior introduced into the reconstructed solution without having any good reason to believe that that's there. Does that make sense? As a result of the over parameterization.
Yeah.
But
Other than that,
that's a
it's quite
great point. The similarity is there, and you were right on in terms of that.
So this is the data consistency thing, is that there's the number of parameters in your discrepancy model equals the number of measurement points. And then for linear problems, this will lead to uniquely identifiable physics parameters, whereas you have a family of solutions. If I have a really rich discrepancy model with a small number of data points, I have a family of reconstructed solutions that I need to choose one from.
Yeah. And since you're talking about interpretability, can you interpret the image that you have on this slide?
It's two pictures from Colorado. Maybe someone recognizes it, the diamond on Long's Peak and the Black Canyon, and then a cool AI generated image that I always just think is kind of neat that someone sent me a year or two ago. I don't know. It's just nice to look at. It's eye candy.
There are people like that in Colorado now?
Yeah, all over the place.
Okay.
Thank you so much. Do we have any other questions, comments? I don't.
Yeah, actually, I might have one. Hi, my name is Sasha. I'm postdoc with the Crunch Group at Brown. And pertaining to the last issue that we talked about, the data consistency term. So for this data consistency, you need to choose a parameter that has something to do with the number of standard deviations you go away from the data, was what I understand. And you choose that based on how this parameter defines a belief into how much you believe into your physical model. That's what I understood. So my question is, what's the typical belief that you have or that you need in this data consistency term?
You guys think much more Bayesian than me. The data consistency is just saying that if I have a discrepancy model, which is a constraint force and a discrepancy model are kind of the same thing. I don't know if that's clear from my talk necessarily, but the constraint force is sort of measuring what sort of residual in the system is not explained by choosing the right parameters in my parameterization of the physics. So the constraint force you can think of as pushing on the system to satisfy the data constraint. The discrepancy model you can think of just kind of picking up the slack. It's sort of it's all the same idea. So data consistency says that I have the same number of parameters in my discrepancy model or constraint force as there are measurements taken of the system. So if I have 2 measurements, my discrepancy model has only 2 parameters that I can tune. If I have 100 measurements, there's 100 parameters. So then you're not in situations where I have 1 data point, but I have a discrepancy model that has 1,000 parameters in it, because then you have this potential non-uniqueness issue that's introduced. Is I have a lot of freedom to play around with the residual of the system, but I don't really have that much guidance as to how to do it, and you can potentially end up with non-unique reconstructed solutions. That's the idea. So it's maybe there's a way to connect it to the kind of Bayesian framework that you just outlined, but that's not how I think about it, at least.
Okay, yeah, thank you. That makes a lot of sense. Is it difficult to tune this parameter?
Well, it's done automatically by
Okay.
Let's see. It's done automatically in this problem. So
yeah.
So I'm using the kind of fixed notation from probability here, because again, it's kind of how I think about it. So in this R system of equations, you say, given an epsilon, the solution parameters and the discrepancy model parameters lambda, or the constraint force magnitudes, same thing, are uniquely determined. But I needed an extra condition to figure out which epsilon I choose, right? And that's coming from minimizing the constraint force. I don't know if that answers your question. So it's not,
Yeah, that makes sense.
It comes from solving this system of equations.
Yeah, thank you very much.
Okay, thank you so much. And we've gone over the time, so I think it's time to close the session. Thank you so much for your great presentation. Any comments, George?
No, I just want to say bye and thanks for stopping by, guys.
Thanks so much for having me. I really appreciate the opportunity.
Yeah, thanks for the opportunity. It was great to be here.
We like your pedagogical style, Conor.
Thank you. Thank you. Yeah, seriously, if anyone wants to talk about their work or this, I'd be happy to. So I'll put my email up one more time.
Yeah.
Please feel free to reach out.
Sure.
Yep.
Thank you, everybody, for joining us today, and I hope everybody has a great weekend. Bye.
Bye.